Hello, this is Stephen Neshaba, and I'm here to help you out with the computational lab using automated optimization in Bronsted-Lowry equilibria. The sort of problem that we'll be working with is this one here, given by equation 1. An acid dissociates to produce H plus and A minus, and then there's various other equations that are relevant here that you'll want to be consulting before you come into class. And there is also quite an extensive what to do in preparation for this activity. So you'll want to spend some time doing the pre-lab for this. But for right now, I just want to skip straight to the thing that we're sort of problems that we're going to be doing. Here's problem 1a. At equilibrium, find the value of H plus in the 0.25 molar solution of HA when the concentration of H plus is such and such. So I'm just going to jump over here to Excel, and perhaps you'd like to set up an Excel sheet that's set up this way. As you can tell, I've already set up with the HA initial concentration being 0.25 as the problem has suggested. Okay, assuming you're back. This is sort of the normal thing. I think you can do this on without too much help. I'm going to enter in the change variable. Why don't you do that right now? Okay, I think what I should do is I should say that the change, the amount of HA will be equal to minus whatever's in this brown X box. And let's see, this would have to be the amount of H of A minus that appears will just be equal to whatever's in that X box. And the same thing for the H plus concentration. Okay, that looks good to me. And now you can probably do the equilibrium row yourself. Why don't you give that a shot? Okay, here's what I think I ought to do. I think I ought to say that's equal to that initial value plus the change. And I'll just fill that one straight across too, because the rule is the same. Now, of course, we don't have anything written in for x, but I think I'll go ahead and type in a number just to make sure that all the formulas are working right. And that looks pretty good to me. So now before we go on to the goal seek, which has to do with figuring out what the value of the percentage of the dissociation and so forth, that is, before we go for the goal seek, I may as well set up equations for the rest of this, and you should too. Okay, I think for Ka, that must be equal to the H plus concentration times the A minus concentration, all divided by the equilibrium HA concentration. That looks good. How about the pKa? Well, that's just equal to minus the log of the Ka, so I'll enter that in. And well, why don't you give those two next ones a shot. pH obviously is going to be related to the H plus. Okay, here we go. I'm going to say the pH is equal to minus the log of that H plus concentration. And the pOH obviously is going to be equal to 14 minus the pH. There we go. And the percent ionization, well, remember percent ionization is how much A minus forms relative to the initial amount of HA, which is in that box. So let's do that. That's equal to that amount, equilibrium value of A minus divided by the initial amount of HA. And I've actually already set this up as this box as a percentage using the format command. So now this is what it would all be if x had a value of 0.01, but of course it doesn't. Now let's see what else are we told about this problem. We know that H plus at equilibrium is 4.07 times 10 to the minus 3. That's the H plus at equilibrium, so I'll just go to a goal seek. And I'd like to set box D17 to that value, which we just mentioned, 4.07 times 10 to the minus 3. And what are we going to change? Of course, we're going to just change the X box. And it looks like it found a result. Everything looks pretty good to me. And so in the end, the percent ionization for this problem is 1.63. And all the problems that is in part 1 look a lot like that.